Hey everyone, this is Jeff Mankowski. Welcome back to the Maverick Statistics channel. In our last video, we saw how to compute variances and standard deviations for samples. And in this video, we're going to learn how to do the same thing for populations. And we're going to start by bringing up onto the screen the same two formulas we were looking at the last video. On the top half of the screen on the left, we've got the formula for sample variance, on the right for sample standard deviation, and we're going to learn how to reconfigure the formulas to make them work for population. Now, a really good starting point is to realize inside of our formulas, do we have anything written in that's specific to sample data? And we have a couple things already circled in here. Our X bars are standing for sample average. The other thing that's specific to a sample is it looks like on the denominator we have lowercase n's. Now, n stands for the total number of observations, but again, inside of a sample. So what we're basically going to do is take both of the formulas and rewrite them so that we'll be able to interchange what's circled in blue with the symbols for the same type of thing, but from a population. So in other words, symbols for observations in a population and symbol for the population average. And to get started, we're going to roll out some shorthand. To prepare for population variance, we're going to write in what we call sigma squared. That's going to be shorthand for population variance. And we're going to take basically the same thing we had up here and rewrite it with those changes. So we're going to show the sum of each x value minus, and the x bar switches with a population average. So we'll go ahead and we'll put mu in here. And on top, we're going to put in everything else exactly the same as it was before. On the denominator, instead of lowercase n, now we're going to use capital N because we're talking about the total number of observations, but this time in a population. Now, on the far right side, for our population standard deviation, we're going to write in sigma with no square, and we're virtually going to take the exact same thing that we had on the left, but put it under a square root sign. So we're going to open up that square root sign on the top. We're going to say the sum of x minus, once again, we're going to switch to mu for the population average and write the rest exactly the same. And down here, we're going to put our capital N back in. Okay, so far, the only other thing that we didn't really explain in our formulas was how come when we were working with sample variance and sample standard deviation, we wrote in this n minus 1, but when it came to population, that minus 1 just seemed to vanish. Like if we look downstairs here, we don't see that minus 1 anywhere. Why did we do that? Was it a mistake or did we forget? The answer is no, it's actually something that's very important part of the structural differences in dispersion between data from a sample and data from a population. And to get a better fix on what's going on in there, let's take a look at the bottom part of the screen. And down below here, we've got two different pieces written in, something on the top, something on the bottom. And this all has to do with wages that people are making for part-time work. Now, in the top, it looks like we're proposing that in some town, any town in the United States, like a fictional city, looks like people are making between $5 an hour and $60 an hour. And we're going to go ahead in red here, and we're going to pencil in some wages that people are making, hypothetically, maybe like $5 an hour, $8 an hour, $12 an hour. And we're going to put in tons and tons of observations here that basically represent all the people in the population, $45 an hour, $49, and fill in as many of these as we can. And we could sit here all day long. We could keep on filling in more and more and more data observations, but we kind of get the point. Down below, what we're going to do is we're going to take a sample from that population above of maybe 4 or 5 wage earners. And perhaps we've got somebody making $13 an hour, $25 an hour, $39 an hour, and maybe $41 an hour. And here's what I want you guys to think about. If we look at the data set that's on the top and on the bottom here. That is just what we've written in, all the values in the top going from, the red dots from 5 up to 60, all the bottom ones, 1341. Which of those data sets has a wider dispersion, the one on the top or the one on the bottom? And we'd probably say, well, heck, that's got to be the one on the top. It's so much wider. It goes from 5 to like 58. The one on the bottom is very, very small and compact. It's only going from 13 to 41. So it must be true that the dispersion is much smaller on the downstairs data set for the sample. And we'd be exactly correct if we said that. Now, here's where that gets to be really, really important. If it's happening that we're looking at data from a sample and we're using that information to represent what's going on in a population, the issue is if we know the sample standard deviation is probably going to be severely underestimated, then we know it's off the mark from the true population standard deviation. And that's really bad because we're trying to use statistics as a proxy to estimate what's going on in the population. And if our estimate from the sample is totally going to lowball things, then that's not good. We need to do something to try to recorrect what's happening so that the sample standard deviation comes out a little bit closer to that true standard deviation from the population. Now, all well and good, how do we go ahead and do that? Well, if we look back up in the top of the data sets, where we wrote in both cases and -1 for the sample variance, sample standard deviation, in both cases, we've got a quotient, right? Now, if we go to the denominator and we shrink it by a factor of 1, what's that going to do to the whole quotient? Well, it's going to make it bigger because we're dividing by a smaller number. And that's exactly what we want to do because we'll be taking the sample standard deviation, we'll be taking the sample variance, and that's a way of getting both of those figures to inflate. So they're a little bit closer to the true mark. So to recap, we talked about formulas for the sample standard deviation, the population standard deviation, the sample variance, and the population variance. And in the next video, what we're going to do is get a chance to look a little bit more conceptually at the standard deviation to make sure that we really understand what it's measuring from a practical standpoint. I'll see you on the next video.